Hi, good morning or good afternoon, depending on where you're at. Welcome to our April webinar on flotation. We'll give everybody just a couple minutes to get logged in. And while folks are getting logged in, I'll let you know that if you do have questions throughout the presentation, you'll see on your control panel a question pane, and you can just type your questions in there. And we'll get to those at the end of the presentation. It is 11 o'clock, so respectful of everyone's time, we'll go ahead and get started. As I mentioned, this is the April ACPA webinar for flotation. I'm Kim Spahn. I'm with the American Concrete Pipe Association, and our speakers today are Jennifer Schaff with County Materials and Josh Beakley with the American Concrete Pipe Association. I'll go ahead and turn it over to you, Jennifer, and we'll get started.
It looks like we have a poll question to start off with. Kim, can you help us with that?
Absolutely. So you should see that on your screen. I'm actually going to launch the actual poll, which you should be able to answer on your screen. And we're just curious and wanting to know, what is your area of practice? Are you with a public agency, a consulting engineer, a contractor or developer, a pipe manufacturer, or are you in education or with a university? And you should just be able to click that on your screen. I'm seeing most of you guys are getting the hang of that. We'll have a few of these throughout the session. Give everybody just another minute to answer those. While you guys are answering that polling question, I did want to let you know we do have PDHs that will be sent out following this presentation. Those typically will probably go out sometime next week. So if you don't get it by the end of next week, please let us know. Also, if you are in a room with a group of folks that all need PDHs, if you will send me an email, my email can be found either on our ACPA website, or it is kspahn, S-P-A-H-N, at concretepipe.org. You probably got your registration and information from me. Looks like people are still getting logged on here, but we'll go ahead and close that one and share the results. So Josh and Jennifer, looks like we have mostly public agency and consulting engineers, with 30% with public agencies and 51% as consulting engineers.
All right. Very nice.
So Jennifer, back to you.
Great, thank you, Kim. I am trying to forward my slides here. There we go. So welcome, everyone. Thank you for your time today. Josh Beakley and I will be giving a presentation on pipe flotation that will take about 45 to 50 minutes. We'll then open it up for questions, and we'll have some questions for you also. So let's get started. So our outlines for today, we're going to talk about why do we care about pipe flotation? What is buoyancy? We'll cover two different methods to account for this in our designs. We'll have a short discussion about factors of safety, and we'll walk through some example problems and give you some rules of thumb to use as you're designing your own project. Flotation failures, why do we care? None of us wants to see this on our projects. Not every flotation failure looks like this, but buoyancy can be a powerful force, and even if the resulting effects aren't as dramatic as this, it can still cause a lot of damage to the infrastructure above and around the pipe, resulting in major repair costs and safety issues. This is a figure from NOAA showing 2019 billion-dollar weather and climate disasters. Pipe flotation is becoming a more common occurrence these days. If you look at the extreme events we've seen in recent years, many of them involve flooding and extreme water levels that are beyond what we typically design for. This is another graphic from NOAA, and they're predicting widespread flooding this spring. Not as severe or prolonged as 2019, but major to moderate flooding in 23 states from the North Plains to the Gulf Coast, with most significant flood potential in parts of North Dakota, South Dakota, and Minnesota. So pipe flotation is something we should be looking at as we go through our pipeline designs and culvert designs. So let's talk a little bit about buoyancy, get some of those concepts down. So what is buoyancy? There's an upward or buoyant force on any object in any fluid. If the buoyant force is greater than the object's weight, it will rise to the surface. If the buoyant force equals the object's weight, it will remain suspended. If the object's weight is greater than the buoyant force, it'll sink, right? The buoyant force is always present. It's kind of like the tagline from a Star Wars movie, right? The force is always with you. So whether the object floats, sinks, or is suspended in a fluid, buoyancy force is there. So let's watch a quick video about how we calculate the buoyant force and Archimedes' principle. Kim, can you play that for us?
Absolutely. Let me get that pulled up real quick.
Thank you.
And you guys should all be able to hear this through your computers. So if your computer speakers are not turned up, you might want to turn those on while we play this.
Ships in the world weigh many hundreds of thousands of tons, yet they still float. It does seem counterintuitive to a lot of people. So just what is it that stops these enormous ships from sinking? For the answer, we actually look to ancient Greece. Archimedes was a brilliant mathematician. He wrote many works documenting his discoveries. For us, we're interested in the work called On Floating Bodies, which he wrote as 2 volumes around 250 BC. Within these volumes is a principle that has become known as the Archimedes principle. Any body wholly or partially immersed in a fluid experiences an upward force equal to the weight of the fluid displaced. Now this applies to everything in a fluid. Take this brick as an example. If we lower it into the water, it's going to sink. But Archimedes' principle still applies. Brick is still experiencing an upward force equal to the fluid that is displaced. It's just the upward force is not enough to counter the weight of the brick. You can measure the amount of fluid displaced by either calculating the volume of the brick mathematically or measuring the amount of water that has been pushed aside. Measuring this brick is 20 centimeters, 10 centimeters, and 5 centimeters. The volume is just these 3 multiplied together. And doing that in meters gives us 0.001 meters cubed. This is the volume of the fluid that's been displaced. Looking back at Archimedes, you notice that we need the weight and not the volume. To turn volume into weight, you need to know the density of the fluid. Fresh water is easy to remember. It's got a density of 1,000 kilos per cubic meter. This is why I wanted the volume in cubic meters. We can find the weight of the fluid displaced by multiplying the density by the volume, which gives us 1 kilo. The brick has displaced 1 kilo of water. And Archimedes tells us that the upward force experienced by the brick is the same as the weight of the fluid. So the brick is experiencing an upward force of 1 kilo. Given that the brick itself weighs 2 kilos, that upward force is not enough to overcome the weight, and the brick sinks. To make an object float, we can turn.
Jennifer, can you mute your on your end? I'm getting some folks saying we're getting double background noise. It looks like Josh is muted.
Thank you, Kim. So let's bring the discussion back to pipe materials. Looks like I might not be showing my screen here. Kim, are you able to see my screen? Can you confirm?
Nope, not yet. Should have asked you
Okay.
if you wanted to share your screen.
Thank you. So now let's look at the propensity of common pipe materials to float. Most plastics have roughly the same density of water, just slightly less, 60 pounds per cubic foot versus 62.4 pounds per cubic foot. Concrete density is roughly 2 times that of water, and steel density is roughly 7.5 times that of water. So if you took a rod of plastic and you dropped it in water, it would float. Conversely, if you took rods of concrete and steel and you dropped them in water, they would sink. We've all heard of the ASCE concrete canoe competition, right? Similar scenario, if we took a brick of concrete and we put it in water, it would float. If we hollow it out in the shape of a canoe, it will float. Remember, objects just need to have a greater ratio of empty space to mass than the fluid. So let's talk about some pipe weights. So if you have an empty pipe, it's not just the density of the pipe wall material that matters. We also have to consider the weight of the water that it will displace. That's the buoyant force, right? So if we take a 48-inch diameter concrete pipe with a wall thickness of 5 inches, it would displace a volume of about 18 cubic feet per foot. Multiplying that by the unit weight of water results in a weight of 1,145 pounds per foot. For the sake of a simple comparison, we're going to assume that the pipe materials shown displace that same volume, although admittedly HDPE and steel would take a less volume. So let's take a 48-inch diameter HDPE pipe. It would weigh roughly 26 pounds per foot. Compared to the weight of water, 1,145 pounds per foot. Again, this is that amount that it displaces, that buoyant force. And we assume that that pipe is sealed, empty, no soil above it, then it would definitely float, right? A steel pipe weighs roughly 48 pounds per foot. So it's pretty obvious under the same circumstances, nothing inside the pipe, nothing above it, it would float as well. For that matter, even an empty concrete pipe would float. So we have a poll question number 2, Kim.
Okay,
Which
poll question number 2 coming up.
Okay.
Okay, you
So which
should be able
material?
to click right on your screen. I had a couple of folks ask the question last poll that they couldn't answer.
Okay.
So you should just be able to click right there on your screen. Which has the highest unit weight? Concrete, metal, plastic, or wood? Give everybody just a few minutes. Hopefully everybody can click this time. Could have had something to do if you joined after we launched the last poll. I'm not sure. Okay, voting is slowing. So I'm going to go ahead and close that.
Okay.
Share the results. And we got 58% that said metal, 42% said concrete.
Ooh, trick question there, huh? All
Yeah.
right.
All right, back to you, Jennifer.
All right. So now that we talked about the different pipe weights, let's think about this flotation calculation. Of course, we're talking about buried pipe today, so we have the benefit of a soil load on top of the pipe to help hold that down. We only need to worry about pipe flotation when the pipe is buried under shallow covers. However, as engineers, it's up to us to determine how shallow pipe can be buried before flotation becomes a concern. And as we do this calculation, we're going to look at balancing the buoyant force, which is attempting to push that pipe up, with the vertical soil load pushing the pipe down. And we're going to include a factor of safety in there, which we'll talk about in a little bit. So let's think about this microstructure of soil that we're relying on to push that pipe down. If we sweep the cobwebs out of our brain from soils class, we'll remember that we have a phase diagram to describe the structure of soil, and it's composed of solids, water, and air. If a pipe is buried in soil where the only void space is filled with air, there's no concern for potential of flotation, right? Because that buoyant force only exists when an object is in a fluid. However, if the voids are filled with water, then the pipe has an upward buoyant force. Additionally, though, the soil itself opposes less of a downward force because of the buoyancy effect on it. So we have to account for that in this calculation that we're going to do. And we're going to do that by using a buoyant weight of soil, which is going to be equal to the saturated unit weight of soil minus the unit weight of water. What a mess, right? So we can see in this photo that it looks like all of our void spaces are filled with water. So how do we calculate this before it happens? Let's walk through a couple different methods. In both of these methods, the difference between the two is how we calculate that soil resistance for buoyancy. You'll see when Josh goes through the examples that we're following the same procedure. The only difference between the two is how we're going to calculate the soil resistance. So that first method is defined by the ACPA Design Document 22, Design Data 22. And this is a handout that's available if you go to the toolbar. Kim provided it there for you. And this is often referred to as the column method. The second method that we're going to talk about is the Watkins-Moser method from Utah State. And this method is a little less conservative, and I'll offer you a little bit of history about Watkins. You'll see in the screen there's a photo of him teaching pipeline students at UT Arlington. So Watkins graduated from MIT with a master's degree, and he really wanted to study structures and bridges, actually. But the nation was still recovering from World War II at that time, and bridges were of low priority. So he ended up joining the faculty at the Utah State Agricultural College, and his emphasis was on water distribution in the arid Great Basin. So besides his teaching assignments, they had asked him to assess irrigation canals. And interestingly, he found that the canals lost a third of their flow per mile due to precipitation, infiltration, plant growth, and rodent activity. And he was also depressed by the fact that there were a lot of children that died in these canals as they were trying to play in them. So he thought, you know, if we could use buried pipes to replace these channels, it would probably be safer. So he took a sabbatical, and he went to Iowa State, and he studied buried pipes under Spangler. And he graduated with a PhD there in 1957. So as we talk about his methodology, he has more of an ag background, and I think that's why his method is a little less conservative. So let's look at those equations and the information that we're going to need to have as we start to look at calculations. So we're going to need to know the depth of cover on that pipe. We need to know the outside diameter of it. We're going to need to know where that water elevation is, whether it's the groundwater that we're accounting for or some other arbitrary groundwater elevation. Maybe we're planning on jetting those trenches. And then we're also going to need to know the saturated unit weight of the soil we're dealing with. So the first method, remember, this is also called the column method. We are going to calculate the soil in a column directly above that pipe, and that's depicted in the dashed lines that you see extending to the surface there from either side of the outside diameter of the pipe. Sometimes this is referred to as the prism load, and it's equal to the depth of cover times the outside diameter. And then we're also going to include the haunch material above that pipe, and that's represented, we're going to take the area of a square, right? I was going to say rectangle. The area of a square DO times DO, and we're going to subtract the area of that circle defined by a diameter of DO, and we're going to divide that by 2. Sometimes in literature, you'll see that area defined as 0.1073 times DO. So that's that method. The second method is the Watkins-Moser method. And you'll see here that in addition to that prism load, that soil resistance is going to include the weight of 2 triangles of soil that flank that column load, defined by the internal angle of friction. So we have soil resistance equaling the prism load plus the area of those 2 x's that you see in your screen there. And we end up with this Brangus of an equation at the bottom. That's what I call it. And we're not going to dive into the geometry of how to solve that today, but I included a little bit better picture for you. Let's see if I can get it to come up here. So this is a diagram that I took out of Buried Pipe Design 3rd edition, and you can see that soil wedge is really well defined here, again defined by that internal angle of friction of the soil. This book is available online free of charge if you are an ASCE member through Access Engineering. So I included a screenshot of what that looks like. So if you're an ASCE member, go in and log in, Google or in the search bar put in Access Engineering, and you'll get to a screen that looks much like this, and you have access to all different kinds of books, spreadsheets, and case studies. So check that out. And if you're not a member, maybe this is a reason to become one. Poll question number 3, Kim. Which method accounts for a larger value for the soil resistance?
Okay, all things being equal, pipe size and installation conditions, which pipe material is least likely to float? While you guys are answering, I saw a really cool comment in the question pane that someone had Dr. Watkins at USU in '92 and still has his notes. Oh, that's kind of cool.
Really? That's very cool.
Okay. Looks like the poll is stalled, so I'm going to close that, share the results with you guys. Jennifer and Josh, we have 68% said concrete is least likely to float, 25% said metal, and then the bottom 2 were plastic and wood, split 5 and 3%.
Okay, now who really said wood in this thing? Come on now.
Maybe they thought that it said most likely to float.
Maybe.
All right, well, let's talk a little bit about factors of safety before we get into some example problems here. In some instances, we're going to find that the downward force of the soil is going to offset those buoyant forces. And we know soils can vary significantly over a job site. So how much variability is there? In other instances, the weight of the structure will be enough to offset the buoyant force. The structure weight should be less variable, right? So that seems like it would be maybe less of a factor of safety there. So as we analyze our designs for flotation potential, what type of factor of safety are we going to look to? So let's look to our structural engineers and our geotech friends to see what they're using in terms of guidance we might be able to borrow on structures. So I included a few of those factors of safety for you to look at. So slope stability, we're looking anywhere from 1.3 to 1.5. When we get into those foundation analyses, we're looking anywhere from 2 to 3. That's a pretty significant safety factor, or factor of safety, in my opinion. And when I think back in my consulting career, when we used to design bridges and structures, we tended to do a much more robust and spend more money on the soils investigation there than we did, for example, like subdivisions. So as we talk about these factors of safety, keep in mind, you know, how much reliable information do we have to base our decisions and our designs on? So Josh, do you want to kind of offer to us what you think, what you see in terms of factors of safety that are associated with flotation?
Sure, and you and I have talked about it, you kind of alluded to it in that previous slide, and that, you know, factor safety really comes down to, and you may want to even call it load factor, depending on how you apply it to the equation, which you and I'll bring up later, but it really comes down to how well you know the variable you're using in your equation. So, you know, we have two different methods we're talking about today, and obviously I think the one that has less reliability on the soil should probably have a lower factor safety than the one that has the higher reliability factor, the safety on the soil. Do you want me to put out a number, or do you want me to just show it later? We'll get to the
Lay it out there for me, Josh. Give me a number.
I'll lay it out there for you. In general, we've suggested a 1.25 factor safety for when you're using what we call the column load, but you know, basically looking at a soil prism. It's really not much different than if you were designing your pipe and you had the 1.3 vertical load for the earth load going down on it. It's a very similar load factor in that sense. When you come out and use the Watkins-Moser method, at least what we're calling the Watkins-Moser method, when you need that soil wedge actually adds almost double the amount of soil resistance you're calculating. So you should up the factor safety, especially since it relies on soil friction, which is another tougher unknown. So we figure you should have a factor safety around 2 or something like that.
Okay, great. And we'll see that in your example problems later too. So if you didn't get a chance to jot that down. I wanted to just point out in this picture, we appear to have an interim condition. Most of the infrastructure is in place. You can see some curb and gutter back there, and there's an inlet. And there's a lot of grass growth here, so I'm guessing that this is a phased project. So I wanted to point out, you know, a lot of times when we install pipes, we end up creating this temporary, I call it bathtub condition. So we excavate a trench, and in my area of the world, oftentimes those existing soils are clays, and we bed and backfill with a much more permeable soil or aggregate, and we create essentially this bathtub that we're going to put a pipe into. So as we work through designing a project, we need to be mindful of this bathtub condition as it relates to phasing and construction techniques. For example, are we allowing the contractor to jet these trenches to achieve consolidation? Is this an interim condition where this is going to sit and we're going to have potential for those trenches to fill up with water, and this is an emergency access during construction? So just some things to think about in addition to your flotation calculations as we move forward here. And we'll talk about a few other things. So in this picture, Josh, walk me through what you'd use for a factor of safety here.
Well, you know, and in our examples as well, you know, you have to kind of figure out first whether you're going to assume the water table is a certain level below the soil or equal to or above the top of the surface. Well, this one's pretty easy to understand that the water table, in this case, is going to be above the surface. Factor safety doesn't change. I guess just your concern, you know, the depth of height of fluid is going to be what really concerns you, but you're still using basically 1.25 for the column method, and we use 2.0 for the Watkins-Moser method.
Okay, very good. Thank you.
And it's,
so Josh, run us through some examples now, and you'll see as you go through those that we're going to kind of follow the same methodology where we're calculating that buoyant force to see if flotation is a concern. We're calculating that soil resistance, and then we're including that factor of safety in there. So go ahead, Josh, please.
All right, thank you. Can we all see the example RCP shown on my screen now?
I think we're maybe a second delayed. Yep, now we see it.
All right, awesome, thank you. Yeah, so we're going to go through some examples showing some of the philosophy that Jennifer was talking about it and teaching us. So we're going to do 3 examples, starting out with RCP. We're going to touch upon metal and plastic as well. Sorry to disappoint some of you, but we won't be doing any wood pipe today. But we will be doing 3 different pipe materials, just to kind of give a comparison and actually give us a better experience in terms of getting some good practice in. So we'll go through, we'll check out our buoyancy force on those pipes, the soil resistance provided to help keep those pipes from floating up, and applying the factor safety and what we're calculating. So these are all going to be 48-inch pipes. Once again, concrete, metal, and plastic. We're going to put them 1 foot below the surface, which is admittedly relatively shallow. And in fact, in some cases, AASHTO wouldn't even allow you to put it 1 foot under the surface if the plastic pipe on the pavement or something. But in general, sometimes people get desperate and have to put pipe on that shallow. So it's going to be 1 foot under the ground. It's going to have we're going to see the water table at the surface. So I'll start out with a 48-inch pipe, outside diameter of 58 inches. We're going to put it in feet so it's easy to calculate. We evaluate our fluid weight in pounds per cubic foot. So that's the parameter given. Now we're going to first figure out what our pipe weight is. In this case, it's going to be 867 pounds per foot. You can relatively easily find that value on our website, American Concrete Pipe Association website. Just look it up in the ACPA Concrete Pipe Design Manual, and you'll find our pipe weights. In this case, a 48-inch pipe is 867 pounds per foot. Couple parameters we'll need in terms for our calculation purposes are the saturated weight of soil, 120 pounds per cubic foot, and we need to know the internal angle of friction if we're going to use the Watkins motion method. Now, the 120 pounds per cubic foot, admittedly, that's a little bit light for a saturated soil. Maybe 130 might be a little better, but we're just kind of erring on the conservative side here and using 120. So as flotation concerned, we know our pipe weight. We'll figure out the displaced volume of water and find the weight of that, which is 1,145 pounds per foot, and subtract the one from the other, and you get a negative 278 pounds, which is subtracting the weight of the water from the weight of the pipe. Now, negative value means that you can anticipate that that pipe is a buoyancy force, and that's what BF stands for, buoyancy force. So we have a buoyancy force of 278 pounds per foot pushing upward. Now let's see what kind of resistance we can get from our soil to help us keep that pipe from floating. We start out with the column method. We have it here in our PowerPoint, and if you ever need to look it up, once again, that's another one that's in our concrete pipe design manual as far as the equation. We're taking that 120 pounds per cubic foot saturated weight, subtracting the unit weight of water, and multiply by the 1 foot of fill, include these upper haunches in our calculations, and we come out with a soil resistance of 423 pounds per foot. So that's how much additional resistance to flotation we're going to get from the downward force of the soil. That was using the column method. Now, if we use Watkins motion method, we're going to actually have that soil prism along with those soil wedges. So the soil prism itself we have, and we calculate for those soil wedges by incorporating that angle of internal friction to figure out this slope here. And we come up with an area for the wedges, gives us a number of 388 pounds per linear foot. So as I mentioned earlier, you get almost twice as much soil resistance using the Watkins motion method as you would using the soil column method. And not to mention, the Watkins motion method takes a little more time to calculate in the end, right? Because you have to calculate the wedges. So most people, we bring up both these methods because obviously Watkins motion method is out there in textbooks and things, as well as the column method is out there. So we want people to see both of them, but I can tell you as a recommendation, we would recommend simply using the prism method, which if you look around these days, most pipe industries anyway are promoting the prism method as well. So we're not the only ones out there promoting that, but we are showing you both methods. Now, when you get to that point, now we have to apply these factors of safety. I call it factor safety, maybe I should call it a load factor. Jennifer and I have discussed this a few times. We're taking this buoyancy force, and I multiply it by a factor safety. In reality, I'm kind of like applying load factor here to be conservative in our analysis because of the unknowns we don't know, the soil properties. We take that buoyancy force, add it to the resistance, and see what the net result is. If it's positive, that means the pipe should not float. If it's negative, it means you can expect the pipe to float. Now, Jennifer, you know how to talk. I know you think perhaps maybe we should look at factor safety on the other side of the equation. You have any thoughts on the shares on that?
Yeah, my initial, when we were going through this, putting this together, I would think that you'd want to apply that factor to safety to the resistance of the soil, because that would seem to me to be much more variable than that buoyant force.
Yeah, and that's fine, and it makes a lot of sense. And you got me thinking about it quite a bit myself. And it's kind of funny. We talked. I mentioned to you that I think it's maybe an old versus new philosophy here, and that most of the structural engineers these days are, if we're used to designing, say, for the LRFD method, LRFD load resistance factor design method, we're applying load factors to the load, and the load in this case is really the buoyancy force. So probably a better way of saying it's really applying load factors to buoyancy force and analyzing versus the resistance, or in this case, the resistance comes from the soil. So, but either way, a slice you're coming up with an appropriate answer. So if we come up and we compare the two methods, Watkins-Moser looks a little more conservative, and it's really only more conservative because we applied a higher factor safety to it. ACP method gives you 75 pounds net force, Watkins-Moser gives you 255. In either case, we're showing the pipe does not float. We have the same buoyancy force for each. Watkins-Moser has a little bit higher soil resistance force to it. Ooh, okay. We have another poll question. And this is sort of a trick question too, I'll warn you. So it just kind of depends on your preference, I think.
Did you make all these trick questions, Josh?
No, that last one was kind of a trick. You can do this poll question. While you're doing that, I'll mention kind of that one where people had it was like 50-50 between concrete and metal. Okay, is the poll? Okay. Because I'm not seeing poll questions. Is poll questions open there, Tim?
Yeah, it's launched. So which flotation design method assumes a larger value for the soil resistance? ACPA column method, the bar method, Watkins and Moser method, or the numerical method? Give everybody just a couple minutes.
Yeah. Okay, and I'll be first to apologize. You folks are totally confused now because our polling questions that we show on the slide are actually in different order than what we're seeing, what Kim's popping us for. My apologies. It doesn't really matter. We're still interested in your answer, and we're still going to learn something from this. But it's kind of funny. The polling questions are a little off target here. All's well. And while we're looking at that, let me explain. We had the poll question, and we asked what was heaviest, and we got 50-50 between concrete and metal. Well, the question was what was the heaviest material. In that case, it's metal because it's 490 pounds per cubic foot. So that was really the correct answer for that question. Some of you may have been thinking, what's the heavier pipe? In that case, it is concrete because concrete's just got a much heavier and thicker wall. And we'll see that in the next design when we go now for metal pipe. We'll see the metal pipe's a lot lighter just because we use less material.
Great point, Josh. All right, I'm going to close this poll and share the results with the audience. And since you guys can't see the speakers, you got a 83% Watkins and Moser method, 12% ACPA column method.
All right. Okay, so our next example is going to be CMP, corrugated metal pipe. We're going to take the same conditions now and run them through the metal pipe to see how that works out. As I mentioned, metal, in this case steel, is a lot heavier than concrete, but in terms of pipe itself, it's a much lighter pipe weight. They have a pipe weight of 48 pounds per linear foot for a 48-inch pipe. Now, metal pipe values, you can find them in the National Corrugated Steel Pipe Association, Corrugated Steel Pipe Design Manual, so you can find them online as well if you're looking for the metal pipe weights. We picked the 48 pounds per foot. Metal pipe weight can vary a little bit depending on the coatings you're using. Kind of a basic weight for it. You start adding coatings, it will get a little bit heavier, but not drastically so. We assumed a 2 2/3 by 1/2 inch corrugation, so I used an outer diameter of 49 inches for this one. So it is displacing a little bit less area, so the buoyancy force will be a little bit less. Same conditions in terms of our saturated soil weight and the soil property and internal angle of friction. So as I mentioned, this one displaces less water. If anyone can recall, I believe we were around 1,100 pounds per foot of water that would be displaced by a concrete pipe. In this case, it's 817 pounds per foot displaced by this metal pipe. Net buoyancy force, however, is much higher because the pipe is so light. So our buoyancy force in this case is negative 700. It's 69 pounds per foot. So that's a pretty hefty buoyancy force when we push up on that pipe and make it push up to the ground. So let's see if the ground can handle all that buoyancy force. Let's go take a look at some numbers. ACPA method, we have the soil prism here. ACPA method, column method, whatever you want to call it. We run through those numbers once again, subtracting water out of the saturated soil weight. So this might actually be heavier in some cases than what you're used to using, but multiply with 1 foot of fill and incorporate the upper hunches. We have a soil resistance of 338 pounds per foot. Now, if I recall correctly, that previous slide, our buoyancy force was higher than that. So it's starting to look like this pipe's probably going to be a floater. We have a floater, folks. Okay, and the next one, Watkins motion method. If we check this one and incorporate the soil wedges, we'll look at it, and once again, we have the soil prism load, and now we're going to add that soil wedge. And as mentioned before, it makes roughly twice as much. So if we take a look at that, gives us a total force of 645 pounds per foot, counting for these soil wedges. We toss it all in together, and whether you apply a factor of safety or not, you're still going to find that that pipe has a net negative force, which means it's going to go upward, which means your pipe is going to float out of the ground if you don't have 1 foot of cover over it. In this case, this metal 48-inch metal pipe will float through the ground. So that would be something you want to be concerned about, and we'll talk about a little bit later here, maybe ways of tying it down or other pipe options, really, but one or the other. One more shot here. We're going to do plastic. Now, if metal pipe floated, what do you think the plastic pipe's going to do? Well, we're going to run the numbers anyway, just to give us some experience here. Same philosophy. In this case, it's 48-inch pipe. It's got a corrugated outer diameter. Outside diameter is 54 inches. I split the difference and used the median outside diameter since it is corrugated, and used 4.25 feet for the outside diameter. Now that weight you can't really find in too many places. So that's a little more difficult. When you look for that weight, in my case, I calculated it based on the wall area of the pipe itself. If you can look in the corrugated plastic pipe drainage handbook from the PPI produces, which is pretty good material, but they do not have pipe weights in there. Although the interesting thing about it is they are one of the few manuals that actually does kind of have an idea or an example of buoyancy force in their manual. And the interesting thing is in their manual, they pretty much tell you plastic pipe weight is so small, at the end of the day, if you ignore it, it doesn't matter that much anyway. So if you don't feel like looking up the number for your pipe weight for your plastic pipe, it's only 20-some pounds anyway, just ignore it. It's just a small portion of the resistance because the soil is giving you most of the resistance. So you can cut your calculation a little short if you want to do it that way. But we're going to go through it anyway and use the pipe weight as we do with the other materials. Pipe weight of 26 pounds per foot displaces 885 pounds per foot of water. Net buoyancy force of negative 859 pounds per foot. We run through these methods, and we come through here. Soil prism load is 356 pounds per foot, similar to what the other ones gave us. For the prism load, Watkins motor is 681 pounds per foot. Once again, neither one of these are nearly as much as that buoyancy force we just saw. So at the end of the day, we would expect, these pipes are going to float, whether you're analyzing with the ACPA method or the Watkins motor method. So you see in all three examples actually as well that we got this end result the same. Concrete pipe Let's see if I have the next slide. Concrete pipe didn't float. The plastic and metal pipe did, regardless of which method you analyze. So, you know, you run the numbers, we run for the cover, you're looking at something like this, which is something you don't want. You know, I mentioned AASHTO in a lot of cases doesn't even allow one for the cover. But it is interesting, the AASHTO and the LFD bridge design specs does tell you need to evaluate for flotation. They don't tell you how to do it, but they do tell you in section 12.6.1 that buoyancy and flotation needs to be considered anytime the water elevation is above the inverted pipe. So this is good information to have. You have to worry about that. This is the Watkins motion method, same net result. So how much would you need to keep those pipes from floating up? We saw concrete pipe, if you look at the ACPA method, only in this case from the upper row here, we saw with the 48-inch pipe, 1 foot of fill, it would not float. You can get down to about 0.8 feet of fill before that 48-inch pipe would float. The CMP and HTP, they were floating 1 foot, but if you had roughly 3.7 feet over the CMP or 4 foot over the HTPE, you could keep them from floating. Interesting thing, Jennifer pointed this out to me as we were going through this and preparing this, was a good rule of thumb for plastic pipe is to roughly have the same amount of fill height above the pipe as the diameter of the pipe itself. So in our case, we had a 48-inch diameter pipe, 4 feet diameter. You need about 4 feet above it to keep it floating. If it had been a 36-inch pipe, you would need roughly about 3 feet of fill to keep it from floating. You might want to run the numbers, but nonetheless, back of the envelope kind of thing, good rule of thumb, just to think of it in those terms. We don't have the same kind of rule of thumb for concrete pipe as that, so, but we do provide you with a table in this presentation so that those of you who get the slide in this presentation later, you kind of see roughly how much fill you need over the concrete pipe to keep it from floating. And one other thing, and we're going to talk about some other things. I know Jennifer's going to pick up on some other key aspects of flotation here, but definitely we see a lot of people when they get shallow fill trying to make up for that cover by using an elliptical pipe, elliptical concrete pipe. Well, the really cool thing about elliptical pipe is it gives you the same flow area, but it's got a wider diameter, right, or a wider span, I should say, which means it has more soil above it. So it tends to have a higher soil resistance. So elliptical pipe comes out even better for equivalent flow than a circular pipe. So if your circular pipe wasn't going to float, the elliptical pipe wouldn't float either. You will not see in this presentation because of limited time, but we have done an elliptical pipe example for you in this PowerPoint. So if you download it after this presentation, you'll see some examples, or at least one example of how to do elliptical pipe. And we provided you the displaced area for both elliptical and arch pipe. We folks use arch pipe in other parts of the country. So we got a lot of extra stuff that Jennifer and I piled into the back of this that you won't see today, but will be available to you. Okay, one other poll question, and I can guarantee you it won't be the same as what you see on my screen, but good luck with your answers, and I'm sure you get it right.
Got these all mixed up, didn't we?
Yeah.
That's all right. Let me launch a different poll question than what's showing right here. And we'll go talk about a little bit about what Josh was talking about there and calculations. When calculating flotation, the factor of safety is applied to either the soil resistance or the buoyant force. Okay, let's close that, show the audience the results. So we had 61% said buoyant force and 39% said soil resistance.
And congratulations, you're all right. I don't know how you want to apply it. This is the way you do it. I'm going to turn it back over to Jennifer this instant.
All right, Ken, do I have the control?
Okay. Coming your way.
All right. So I just wanted to touch on buoyant forces a bit as it relates to culverts. This is something I see a lot in my Midwest market where lightweight culverts are installed without any substantial armoring at the ends. You can see in this picture here, we have 3 pipes, so it's not just a small amount of water we're planning on transmitting, and you can see that they're all out of, discombobulated, I'll call it. They're all out of invert elevation, if you will. And I suspect that some of these are not designed, but they're caused to happen by folks without knowledge about pipe materials. So I would encourage you to reach out to the Federal Highways Administration HDS-5 document. This is available free online, and it's something that I've often reached to during my career doing stormwater and hydraulic analysis on pipes and culverts, a lot of good information. And I'm going to just read for you quick their definition of flotation. So it's a term used to describe the failure of a culvert due to tremendous uplift forces caused by buoyancy. The buoyancy force is produced when the pressure outside the culvert is less than the pressure in the barrel. This occurs in a culvert in inlet control with a submerged upstream end. So you can see their free body diagram. And I really encourage you to reach to this document and kind of do some exploring on your own. But we get uplift that occurs, and sometimes it pushes that culvert end up to make it inoperable, and we end up creating these impoundments with flooding that we didn't intend. So we can have that condition occur as well when we get blockages to culvert pipes. So you'll see this is a picture that I took in our Iowa market actually of a nice big branch that's caught in there. But in urban areas, I've seen culverts blocked by picnic tables and children's toys, and sometimes it even damages the end of that pipe where it gets curled and closed and just isn't operating properly. Oops. Kim, I have a technical difficulty here, so can you help me out?
Sure, it looks like we can still see your screen.
Oh, you can? What do you see?
But it looks frozen. Still the pipe with the log across it.
Okay, can we pass it to Josh and let him advance the rest of the slides?
That went to someone that's not even a presenter. Sorry about that, Jason. Hold on just a second. Getting it to Josh here.
Oh,
So it's attempting to do.
I got slided to Jason. Jeez, I thought you were starting a new movie with Jennifer, Frozen 3.
I know, right?
That's okay. All right. So this is, am I where you want me to be, Jennifer?
I think that if you could go to slide 60, which shows the blockage of the culvert.
Okay. Can you see my screen?
I cannot.
I can see it.
Okay, so I got the blockage. Then the next one was, the next one was the tree pipe coming up through the road, damaging the pavement.
So advance me the next one, please.
Okay.
All right, so we can see uplift in this photo as well. And if you read the Federal Highways document, they say that only flexible barrel materials are vulnerable to this failure because they're lightweight and they lack the resistance to this longitudinal bending that can occur. And you'll notice that the ends of this cross culvert have very little armoring at all. And we actually have 2 pipes here, so it's not like we're taking a small amount of flow. We do need to be using substantial end walls and armoring these culvert ends, particularly when we're having some pretty good flows coming through. Next slide, please.
We're on it.
So there's a number of precautions we can use in order to add some dead weight to these ends. Here's an example of some slope paving around a mitered inlet. A nice install. Next slide, please.
Okay.
And here, it's probably hard for you to get perspective, but we have some pretty steep fill slopes, and we've got some good riprap protection around this end. We've got a nice head wall and good end walls to protect from erosion. So that's a good, that one gets a star, Josh. Next
All
slide.
right. Excellent.
So we can also turn to anchors. This is a photo that I took in Myrtle Beach. There's a lot of these pipe discharges right along the beach, and they all have this kind of anchoring system. And I suspect there's some concrete or some kind of dead weight underneath these, but we can also use concrete or sheet piling cutoff walls, some good heavy head walls. All of those provide anchorage. We do need to make sure that that culvert barrel end is securely attached to the anchorage devices in order for it to be effective. And this helps protect against that inlet bending and warping. Next slide, please.
Okay. Well,
So this is a
Okay,
video.
Josh, and I'll turn on the video on my end so that everybody can see it. If you guys will, sounds like you guys will have to mute Jennifer, and then you can tell us about it following it.
Okay. You let me know when it's running. This is a video that Brian Remsen, our Iowa City plant, was kind enough to share with me, and it's just an awesome video. I really like it. Are we playing?
Working on loading.
Okay. It's not very long. So what you're going to see is there's a gravel road acting like an impoundment, and it's backing up a considerable amount of water. And Brian did a great job of giving us kind of photograph of what's going on here. You'll notice that there's not a lot of cover over the pipe. Again, this is a riprap or gravel entrance, and there are significant forces of water coming through these pipes. And you can see at the ends, it looks like we probably need to put some riprap or end walls on these, but they are just passing the water just fine. And holding in place. We don't see any washout here.
Okay. Looks like it brings us to another poll question.
Okay,
All
and
right.
in good form with the rest of our presentation, I slid one extra one in here that I'm going to launch before we get to that last one showing on your screen.
Oh, no.
The question is, do you think it's important to have proper flotation design in your specifications? Yes, no, or it's not necessary. My area doesn't experience high water.
And while they're answering that, I want to bring up a couple more things about our presentation. You know, we've shown some examples and discussed the water table up to the surface level. We do have an example in this presentation further back about when the water table is somewhere in between the top of the pipe and surface. So we have an example of that for you. We even touched a little bit on flowable fill with some ideas on how high up you can go with the flowable fill before the pipe starts to float as well in the back of this. So try to give you a little more extra for the money.
Hey, Kim, I'm getting a message that the audio is.
Yeah, you are cutting out a little bit, Jennifer.
Okay.
Must be your technical difficulties.
Okay.
I can hear you saying okay, but so the response to that was 92% said yes, 5% said no, it's not important, and 3% said not necessary because they don't experience high water. I might have answered that with the no, not necessary in Colorado. I mean, we typically don't have a whole lot of water and flooding until 2013 when we actually had a ton of flooding up in the mountains. And so I think even in areas that don't have typical flooding, it's still important to consider what may happen in a larger storm, 100-year or 500-year storm. So, but I'm glad to see most of you said yes. And then we do have one last polling question for you guys. So with 92% saying yes, if it's not in your specifications, we would be happy to help you write a specification around proper flotation calculations. So would you like to have ACPA be contacted by ACPA to discuss adding or improving your flotation design in your specifications? And while you guys are finishing up this polling question, I know we're right about noon, and so we do want to be respectful of everyone's time. I do have a couple of things to go over in conclusion of this that you might be interested in, and then we'll stay on and we'll answer the questions. We've got a lot of good ones that came in that I saw as the speakers were talking. So the last few announcements I wanted to make was, one, PDHs will be available. Probably get those out to you guys by the end of next week. If you don't get it by then, please let me know. Second thing would be, if you are in a group and multiple people need PDHs, you'll have to email me. And the invitation and confirmations from this webinar came from me, so you can just reply to those and let me know that you need multiple people with their names and PE license numbers if you guys need that on your certificate. Another announcement there on your dashboard, Jennifer mentioned it during her presentation, that design data 22 can be found. So if you look under handouts, you should see handouts on your dashboard. You can see DD22 right there and download those calculations that Josh went through. You can also find that on our website if you don't catch it before this ends. We will also post this recording and a PDF of this presentation, so you can have the slides as well. Yeah, you'll get a reminder email following this with the location of that on our website, but it's basically under education, then webinars. And then finally, and last announcement before we move into questions, is our June. We do these every other month. So the next one coming up will be in June. We're going to be talking about innovations in concrete pipe. So be looking for that sometime in May. We'll send out an invitation for you to join us for that one. And with that, I'm going to turn, our polling question said 12% yes, 66% no, and 22% maybe. So I'm guessing most of you guys have this already in your specification and you're set and ready. Josh, I'm going to turn it back to you because some of the questions go back to your calculations, so you may want to refer back to some of your slides.
Sure.
I'm going to just pass it back your way. Nope, it looks like you already got control, so we're all set there. Let me get back to some of these great questions. Some of these you may have already answered, but you could do a second review because they came in as you were talking. So one of them was, what if we are only using gravity loads and not accounting for soil friction? Is 1.0 sufficient?
Yeah, and yeah, I don't think so. And I've talked to some people about that. You know, weight is weight, but you know, it's kind of like if you think of like AASHTO and load factor and stuff. Load factor for water is 1.0 because everybody knows that water weighs. When you get to soil load and someone tells you to shoot 120, what are the odds it might be 115, you know, 110? Like I said, we kind of used a conservative value of 120, which is kind of a low end. But, you know, typically people always think 120 for everything because it's generally what we've gotten used to. When we had a lot of soil are less than that, even when they're saturated, they're not quite that high. So I still think you need a factor safety in there. Because there is some variability within that soil.
Okay, perfect. And I think this is a good slide for this next question. It says, what happens if the ACPA method gives a negative number and the
Watkins-Moser method.
Watkins-Moser, thank you, I can spit that out, gives a positive?
Wow, so if we gave a negative number, I mean, it was going to float, and Watkins said it wasn't, I would trust, be careful, I have a lot of respect for Dr. Watkins and Dr. Moser both, and I know Dr. Moser, you know, a little bit. Watkins, I never met. Moser, I know a little bit. A lot of respect for them, but once again, the factor safety is not there. I would say I tend to just rely on our method. If our method says it's going to float, I'm going to trust it. If it says it won't, I'm going to trust it. You know, I should pull this picture up. We visualize these things, and it's hard to really tell from like the picture because the soil may have came back in, but you don't visualize that soil wedge whenever you go out and you see some of these pipe float. You don't really see that soil wedge that I've seen. Once again, doesn't mean the soil hasn't filled in, but I just I'm not that trusting enough to, you know, I'm an engineer, right? A conservative. If I get anything tells me I might have a problem, I'm going to err on the conservative side.
Okay, and I think this question kind of follows up with that discussion, and that is the factor of safety different for Watkins Mosier?
Oh, no, it's funny. No, and you know, let's be honest, first of all, it's our factor of safety we put in those methods. I'm not even sure what Watkins and Mosier would express for the factor of safety. But we call it the Watkins-Mosier method because Watkins developed it, but it's you know, Watkins got his tutoring under Spangler. And then, of course, Mosier got his tutoring under Watkins. And then, if you're looking further, Dr. Folkman got his tutoring under Mosier. And they keep coming out with a textbook, one after the other, just kind of keeping us up to date with the latest on pipe design. So they're all, these are the gentlemen developing a textbook that we look at to come up with this method. But they're all, it's really the same method, just continues through the different textbooks.
Okay, here's a good one to go with your polling questions, Josh, that kind of trick questions. This one says, but the soil is also typically lighter due to water pushing it up. You might want to expand on that a bit.
Okay, and it looks like Jennifer's back on. I don't know if she can talk to us or not, but you know, that's why we use the buoyancy force, right? I mean, that's why we have the, if you look at, I think I can show which one, like they scream at that very first term, that 120 minus 62.4 or 64.2 is, that is accounting for the flotation force or buoyancy force upon the soil. So we account for that in our calculations. As I say, it's an example, an example in the back that kind of shows, you know, there is soil that doesn't have any fluid in it, and you're going to account for the full force from that soil, full unit weight. But if it's got the fluid, then you're going to have to, we were kind of adjusted for that in the buoyancy unit weight. I can see your head shaking, Jennifer, so that's good. All right.
I agree with you.
All right.
And I agree, you know.
If you agree with me, I must be doing okay.
Right. So the research that I did leading up to that, it does seem like that's a point of confusion for a lot of folks, but that's a common way of accounting for that.
Okay. Here's another question for you guys. Why are you using the thickness of the corrugation rather than the thickness of the metal pipe?
Thickness of the corrugation. I think what they're probably alluding to is, so I used a 48-inch pipe, and then I used a 49-inch diameter for that, which, you know, this isn't rocket science. This is engineering. Engineering is the practical application of science. So I did the practical method I found most practical. And what it comes out to be is we have a 2 2/3 by ½ inch corrugation, which means a ½ inch is going to come out. So 2 times ½ inch is an inch, which makes it 49 inches. Admittedly, I can make it 48 and a half if I wanted to account for the fact that the corrugation go in and out. But that was close enough. That's part of what our factor safety for. This factor safety is for. Right? So I don't have to think too hard. Otherwise, you know, I'd start smoke that come out of my ears or something. So.
Okay. Someone asked, and you might just have to go back to this to clarify their question, what was the outside diameter you used in your equation for the concrete pipe?
Yeah.
I think you did 54, right?
Yes. No, 58. Right? It was 48-inch pipe with a 5-inch wall.
Okay.
Yeah, and I guess we didn't, well, I showed, I think, in the diagram, not in inches, but I showed you 4 point, whatever. Really not, I can't even see my screen right now because I just have to screen later. Yeah, it's 58 inches, because it's a 48-inch pipe with a B wall, 5-inch wall, which is another item you can look up, either an ASTM standard, or you can find that kind of information on a design manual. But a 48-inch pipe, most people or most suppliers are going to supply with a 5-inch wall thickness to make it 58 inches outside diameter. That's what we use. And that was a little easier for us because it's not corrugated, so you can't blame me for splitting hairs here. I just used 58 inches on that one.
Right. I was just going to add, most manufacturers have tables showing what their wall thicknesses are, so you can reach out to them, whoever's your supplier.
Okay, another great question, or kind of more of a comment here. Maybe if you guys can agree or disagree with this comment. When looking at scour of the backfill or the embankment, and assuming a complete loss of backfill, be it any pipe material, precast is extremely less likely to be displaced downstream. You guys agree? I
agree. Let's be honest. We know that must have came from a concrete pipe producer somewhere to promote the product, and that's okay. But that's, I guess, the point to be made is, in this day and age with extreme events, at the end of the day, all things being equal, if you lose, if your pipe doesn't float, but for some reason you lose the side support, really what it comes down to is if you lose some of that soil and scour, at some point you might just lose your pipe floating down the stream with it. But concrete pipe, we've seen these examples where it's lost some of that support around it and it still stays there. So it's a much easier fix some of these issues we've seen from extreme events.
And, we could do a whole presentation on scour, but just my 2 cents from when I was consulting, if I had a steep installation, I would always make sure I spec joint ties between at least the end wall and the last pipe section, if not going one more pipe section up. Some people might not agree with that, but that's my opinion.
Yeah, that's good, Jennifer. Thanks. Okay, here's another great question. If the water level is assumed to be at the surface, would it be safe to assume the pipe is filled with water, therefore reducing buoyant forces?
Well, they sound like you're trying to say our pipe leaks. And in actuality, a lot of cases, gravity for a pipe doesn't have to be leak resistant anyway. But if you have a certain, I guess the point is, if you have the water table that high, that would have filled the pipe with water. Joints don't leak that bad usually, and especially like an extreme event and the water table comes up high real quickly, you're not going to have that much flow in the pipe. I don't think anyway, and I'm sure there are instances where it is true, but there are obviously a lot of instances where it's not, because we got enough pictures of them. So.
Okay, we've got a lot of great questions here, so we're going to keep going, and hopefully everybody's learning something as we are. You mentioned using flowable fill to help with weight, but I have witnessed pipe floating in flowable fill. Are you using flowable fill above the soil of the pipe and not directly on the pipe? I'm not sure I understand that last part, but.
Yeah, and it was my fault, but I must have said a little wrong here, but the point was, we've looked at flowable fill a little bit, and basically we want to give you an idea not of how to keep the pipe from floating by anchoring it flowable fill, but when you use flowable fill, the pipe's going to float if you're not careful. If you can see my slides now, it kind of gives you an idea of just the basics of flowable fill, that it only takes a few inches to make a pipe float. I think this particular one, I don't think it mattered much with diameter, if I'm not mistaken when we did this, but basically, even like a concrete pipe, you get up to about 40% of the outside diameter, and you have a potential for that floating as well. So the HDPE and CMP, you have to anchor them down, these floatable fill. Researched it in the Graph did years ago, Dr. Graph did several years ago, found that actually in some cases you can put in a few inches, say, in the plastic pipe and let it cure, and it actually helps to lock it in for the next level of flowable fill. You have to wait for that first level to cure, but The point is you have to be careful with flotation when using flowable fluid products. It's another, it's another method of flow, another Archimedes principle of flotation. Well, in this case, weight is much heavier. We're assuming around 130 instead of 62.4. So it's just a much stronger buoyancy force if you put flowable fluid in.
Okay, great. Thanks, Josh.
My apologies
another
if I
question.
didn't make it clear.
Oh, no worries. Another question is there any advantage to including the pavement section above the pipe to calculate the resisting forces, or is that additional loading negligible?
Do you want to answer that one, Jennifer, so I don't hog this up? Or...
We can't hear you, Jennifer.
I muted myself.
There you go. Now we can hear you.
In my personal practice, if I'm signing something, I'm reluctant to use that pavement area to offset the weight that I need. And I'll tell you why, because oftentimes that installation will sit for a period of time before the pavement's put on. And so I want to make sure that I want to feel confident that my calculation is going to be what I'm going to see in the field. So that interim condition of not having that pavement out there on top of the pipe, I want to make sure that I'm covered. Does that make sense?
I'm looking through to make sure we don't repeat any. Another question was, can a flexible conduit pipe deflecting because of the water pressure or force pushing against the outside of the pipe, giving a course that the installation was not done properly?
I'll give this one a shot, I guess. The way I look at that, and I've heard people, mention that extra force from fluid, but when you think about it, if you have fluid around the pipe itself, it's more of a uniform force, which tends to put any pipe exposed to that in basically hoop compression. So it's not such a big deflection force as it is in general. It's just kind of a uniform force on it. It does reduce, I guess, when you look at a combination with the soil, it does reduce the passive soil resistance. So you can tend to have a little more deflection. Well, we've seen examples where we have the problem exactly because the water table comes up and you lost the side support. So it's not. So you still have that vertical load, and maybe the vertical load might even be slightly reduced from buoyancy, even though the problem is the vertical load. And I'm rambling here, my apologies, but I'm coming around to a point. When you look at the vertical soil load, maybe you subtracted out the buoyancy force, but the buoyancy force is still there as fluid load. So when you add the two together, you have fluid load and soil load coming down vertically. Your lateral soil pressure is now tremendously reduced or greatly reduced because it's a passive soil pressure that relies on how much effective force is coming down from the soil alone and not the water. So your passive pressure does get reduced. So you can have, I guess, some material events where the reflection can be greater. And we've seen it in the Texas fish hatchery where they had some major problems. Obviously, with the fish hatchery, they have a lot of wood around there, and they didn't account for that in their plastic pipe design and had major problems.
Okay. See, two last questions here. One is Watkins versus ACPA methods. Watkins, working with farmers, would be at a 45-degree side by construction method. I assume that's more like embankment style. That's what they're referring to. And then ACPA method is typically shoring like a trench. Would this be appropriate uses for each of those methods?
I see where they're coming from. I mean, it's a pretty interesting way of looking at it. To some degree, I guess, yes, but I just think at the end of the day, keep it simplified and use a column method. I could tell you, for example, we're talking about the Watkins method for flotation. If you look at jacking pipe, and trust me, I'm bringing it back to flotation here in a minute. But if you look at jacking pipe, in the US, we use a soil prison load. In Europe, they use the soil wedge for the vertical load coming out of the pipe, kind of reciprocal what we're doing for flotation here. So it really, different people use different ways of looking at how these soils react. And over in Europe, they actually count for higher soil load on the pipe and jacking because they use a similar method as Watkins motion does. However, in Europe, they also count for the heavier lateral pressure they get from it, so it tends to even itself out in comparison to what we do in the US for jacking pipe. And, you know, in terms of buoyancy force, I kind of feel like it's the same sort of thing in that we're talking about, I guess, splitting hairs and something at the end of the day. The appropriate safety factor, you're probably going to find it both, and they're giving you roughly the same answer anyway. Whew, I turned talking in a circle just to get there, didn't I? My apologies.
All right, thanks, Josh. I just thought this was a great closing question, and is not a concrete pipe manufacturer asking this question. So in simplified view, the best use of pipe would be concrete, followed by metal, followed by HDP, subject to the depth to prevent buoyancy. Question mark. Do you guys agree?
Subject to buoyancy, yes. And subject to most things. I just, I think metal might rust before the place it goes. Other than that, I mean, concrete's still number one. If I'm allowed to say that.
I think it's funny because these questions, as an engineer, like you don't feel like you can just give a yes or a no answer, right? You feel like you need to dive down into every detail about it.
That's a great point. Well, thank you, Josh. Thank you, Jennifer, for your presentation and all your expertise on this. Again, we will have PDHs available going out, and this recording will be posted on our website. We hope everybody can join us in June for innovations of concrete pipe. Thanks so much, everybody. Have a great day and stay safe.
Thanks, Kim. Thanks, Josh. Appreciate it.